Okay, so welcome again for to another video lecture series for Physics 2. So today's video lecture series is on Kirchhoff's rules. So for today's discussion, we will be discussing about Kirchhoff's rules, two terms that often used in Kirchhoff's rules, two statements of Kirchhoff's, the sign conventions for the loop rule, and we will be having sample problems for this topic. Okay, so let's have the definition first for Kirchhoff's rules. So what is Kirchhoff's rule? Kirchhoff's rule is a technique. Uh, this is a technique that can solve or handle circuit problems with greater complexity, which includes several sources, a greater number of resistors, and other circuit elements. Now, the greater complexity referred here in this statement also refers to the idea that when you construct a circuit, you construct a circuit that are um, that might be not limited to basic circuit combinations of series and parallel. So if you create a circuit that are neither series nor parallel, you need an additional set of rules in order to analyze the distribution of currents and the distribution of voltages among the circuit elements present in the constructed circuit. So while the limited number of equations that are limited to series are only used for series. The same goes with the number of equations for parallel. These are limited only for circuit analysis for those types of circuits, while Kirchhoff's rules can be applied for a greater complexity of circuits, including both basic circuits such as series and parallel. So in general, we can apply Kirchhoff's rules to any type of circuit complexity. Okay, so Kirchhoff's rules was developed by the German physicist Gustav Robert Kirchhoff, and this is sometimes referred to, or Kirchhoff's rules are sometimes referred to as the voltage rule. Now, the two terms that we use often in Kirchhoff's rules, we have the junction and we have the loop. Okay, so it is necessary for us to define these terms as we made use of them or refer to them from time to time. Okay, so let's have the first term, the junction. So what is a junction? A junction is a point where three or more conductors meet. Sometimes a junction is also called in some books as nodes or branch points. So in this illustration, as illustrated here in the diagram, point A is considered as a junction, considering it follows the definition that there are three or more or three minimum number of conductors that meet at that point. So C here is A here is a junction. The same goes with B. B is considered also a junction. So since you have three um, number of conducting wires that are connected to it, while C is not a junction and D is not a junction, because the minimum number of conductors that meet at that point should be 3 and up. Okay. Now for the second term, we refer to the next term as the loop. So the loop is any closed conducting path in the given circuit. So for example, in this illustration, we have actually three loops in this diagram. Okay, so the first loop could be this one. This is loop number 2, although it is labeled here. This could be equally labeled as loop number 1, and this is loop number 2, and the outside loop could be loop number 3. But of course, then the labels are could be assigned to any of the loops, such as what you see here in the diagram. The outside loop is labeled as loop number 1. The left-hand window of the illustration is labeled as loop number 2. And the right-hand window of the diagram is labeled as loop number 3. Okay, so when we say we refer to it as a loop, it is any closed conducting path. So when we look at loop number two, for example, this is considered as a loop since you have a continuous round of as a conducting path around this a sort of window in this diagram. The same goes with loop number three and loop number one. Now let's now move on to the two statements of Kirchhoff's rule. So the first statement is called the Kirchhoff's junction rule, and the statement goes like this: the algebraic sum of the currents entering or leaving a node, or leaving or entering a junction, is zero. So what does this mean? Consider a single junction or a junction in the diagram, just like what we have here in this illustration. Junction A. We could also use junction B, but let's focus first on junction A. So what is meant by the statement of Kirchhoff's junction rule is that if you try to get an assignment of signs for all the currents that are entering and leaving the node, and you get the algebraic sum of all those currents entering and leaving the node, the sum or the algebraic sum of all those currents should be equal to zero. Now, for example, if in our assignment, algebraic assignment of signs, we assign all currents that are entering a node or a given junction as positive, while all currents that are leaving the node is assigned a negative sign. So if you're going to add them algebraically, that means you have positive I plus positive I sub 2, or positive I sub 1 plus positive I sub 2, minus the current that is leaving the junction. If you're going to add them algebraically, the sum of those currents should be equal to zero. Now, this idea compounds on the idea of the law of conservation of charge, or the law of conservation of mass, that since the composition of all the current is made up of moving charges or moving electrons. So definitely, if you have these particles entering a junction, there is no way for those particles um, to disappear or disappear at that junction, but instead we expect them to move along any free conducting path, such as this lower wire here. And of course, the conduction of the charges depends on the conditions from which the conducting paths are subjected to, such as when you establish the potential difference between those points in your conducting path. Or example, by establishing the direction of the electric field along the conducting path. Now, as an analogy, try to compare this junction rule of Kirchhoff's to, for example, a water pipeline. So, in this analogy, the direction of the current is represented by the water that is flowing through the junction, and the entire junction itself is represented by the tubings of the wire. So if you have, for example, the water that is entering from both sides of the water pipe, obviously the water that would meet at this junction has nowhere to go, but the has nowhere to go other than the lower water pipe that is connected at that junction. So the same goes with the charges that accumulates at the point of the junction. There is no way for them to stay there, but instead they will be forced to move along the other available conducting path, such as the one that is connected here in this diagram. Okay, so that is Kirchhoff's junction rule. Now, for Kirchhoff's loop rule, now this is the statement: the algebraic sum of the potential difference in any loop, including those associated with EMFs, and those of resistive elements must equal to 0. So correspondingly, the statement corresponds to the sum of the voltages, or the algebraic sum of all voltages of all circuit elements around a given loop. The algebraic sum of those voltages should be equal to 0. Okay. Now, in terms of sign convention, we follow certain sign conventions for Kirchhoff's rule in order to perform any circuit analysis that involves problems such as this one. Okay, so these are the sign conventions for our Kirchhoff's loop rule. Okay, so when okay, so let's go back first with this diagram here. Now, when the statement of Kirchhoff's loop rule says that for any given loop, such as this loop number 2 here, when you consider all the voltage drops of all the circuit elements in the given loop, the algebraic sum of all those circuit elements should sum up to 0. That's the statement of Kirchhoff's rule. Now, let us try to count the number of elements that are present, that are included here in loop number 2. Okay, so of course for loop number 2, we have the corresponding circuit elements. We have R1. This is included in loop number 2. E sub 1 for the first EMF. This is also included. E sub 2 for the second voltage source, or second EMF source. And next is R sub 2. This is resistor 2 is also included for loop number 2. Now, considering loop number 3 has the following circuit elements. We have R sub 2, E sub 2, and R. For loop number 1, the circuit elements included in loop number 1 are the following: R sub 1, E sub 1, and R. So this means R sub 2 and E sub 2 are not included as part of the circuit elements included for loop number 1. Now, once you have identified all the circuit elements included in a given loop, what is said in Kirchhoff's loop rule is that when you have the values of the voltages of each of the circuit elements, so for example, loop number 2, you have the voltage for R sub 1, you have the voltage for R sub 2, you have E sub 2, and you have E sub 1. Given all those voltages, if you're going to add them algebraically, what is meant by adding them algebraically is adding algebraically means that some of the voltages or some of the terms to be added has positive signs and some has negative signs. So this means that when you add them together, it is possible for them to add up to 0. So this means if the statement for Kirchhoff's loop rule says that the sum of the voltages of all the circuit elements around a given loop equals 0, that means there are values in our voltages that would equalize each other in such a way that they would sum up to 0. So this means that there should be items in the given elements that are positive, and there are items in our circuit elements that are negative. So this means that there should be a sign convention that we usually follow in order to assign which among the circuit elements would have voltages that are negative and which among them are positive. Okay, so these are the sign conventions that we assign to all the circuit elements for applying Kirchhoff's loop rule. Okay, so the set of rules corresponds to the rules for power sources, and the other one is the sign conventions for resistors. Okay, so let's have first the sign conventions for power sources or EMFs. Now we consider the first the direction of travel that we assign. Okay, so what is meant by the assignment of the direction of travel is that when you identify a given loop, for example, loop number 2, you will be assigning a direction from which you travel around the loop. So the travel, of course, around the loop is either clockwise or counterclockwise. In this diagram, what we see here is that the loop assigned for loop number 2, the direction of travel is counterclockwise. The same goes with loop number 3, and the same goes with loop number 1. Of course, when you do the travel around the loop, you could actually start anywhere. You could start at node A and going around the loop, starting with R1, then next would be E sub 1, next would be E sub 2, next would be R sub 2, and finally ending up again at node A. Okay, so knowing that, there should be an assignment of the direction of travel around the loop. So for example, if you go over the power sources and the direction of travel happens to be towards this direction, if you do this direction of travel, our assignment for the sign of the EMF for this power source is based on the leaving terminal of the power source. So if you do this travel going from left to right, you are actually entering the negative terminal of the power source and leaving the positive terminal. So whatever the sign of the leaving terminal would be, that would be the sign of the EMF or the voltage source in our equation for voltage loop rule. So just like what we see in this case, the direction of travel is from left to right. Going over the power source means, and you are entering the negative terminal, and you have the leaving terminal as positive. So therefore, the sign of the EMF for this power source is positive. Now, on the reverse, if the direction of travel, as illustrated here, moves from right to left, the entering terminal would be the positive terminal and the leaving terminal would be negative. So therefore, the assignment of the EMF in the equation for our voltage loop rule would be negative. So in summary, whatever the leaving terminal of the EMF from which we leave our direction of travel would be the sign of the EMF in our equation for Kirchhoff's loop rule. Okay, so the next one is for the sign convention for resistors. Okay, so going over resistors, we need to consider two directions of travel. One is for the direction of travel around the loop, and the next one would be the direction of the current that is flowing through our given resistor. So for example, the direction of travel would be from left to right when we go over this resistor as we see here in this diagram. If it happens that the direction of current that is flowing through the resistor moves from right to left, so therefore the direction of travel with respect to the direction of the current are in opposite directions, the assignment of the voltage drop for this resistor would be assigned as positive. Now, of course, the voltage is positive, is also given by Ohm's law. V is equal to I times R. So therefore, the IR term will be assigned a positive sign in our voltage loop rule. Okay, so on the other hand, if the direction of travel reverses, so that means we have the direction of travel now as going from right to left, which is in the same direction of the direction of current flowing through the resistor. This means that the voltage drop, the sign of the voltage drop assigned for this resistor would be assigned negative. So that means if the voltage is given by Ohm's law, V is equal to IR, therefore the IR term of Ohm's law will also be assigned the sign negative. So this means that the IR term would appear as negative in the our equation for equation of Kirchhoff's loop rule. Okay, so I definitely know that it would take you some time to perhaps recall these sign conventions, but of course patience is a virtue, and I am assuming that you will be patient in understanding and reviewing these notes and this video lecture. Okay, so let's take on a sample problem. You have a single loop circuit. The circuit shown contains two batteries, each with an EMF, an internal resistance, and two resistors. So we are asked to find the current in the circuit, and B, the potential difference V sub AB, and letter C, the power output of the EMF of each battery. Okay, so in this illustration, we assign the direction of our travel. It is assigned here as counterclockwise. Okay, so we have points A and point B as the points where we connect our power source. So this is this would be the points B sub AB. For the points V sub AB, we have two power sources. We have 12 volts, a 12 volt battery, and we have a 4-volt battery. Okay, so in order for us to compute for the current in the circuit, we first need to assign the direction of the current. Okay, so normally the assignment of the direction of the current would be considered uh, dictated by the direction of the terminals of how the terminals were connected in our given circuit. Normally, the direction of the current follows the power source with the higher voltage, and the overall direction provided by the power source would be directed from negative to positive. So this means if this is the negative terminal for the 12-volt battery and this is the positive terminal, normally the direction of the current provided by this power source would be towards this direction from negative to positive. So this means that the overall direction around the loop would be towards this direction in counterclockwise direction. Okay, so once you have assigned the direction of your travel around the loop and the direction of the current around the loop, the next step is to apply Kirchhoff's voltage rule. So this means you're going to construct the equation for Kirchhoff's voltage rule. Okay, so for this diagram here, you could actually start anywhere in your construction. So in this diagram, okay, so perhaps we could start with a 12-volt battery. So in our construction, we will have the sum okay, so the sum of all voltages should be equal to 0. So from here, the equation of Kirchhoff's rule, you will be constructing your working equation based on the given diagram. So starting with the 12-volt battery. Okay, so recalling the sign conventions, the first element that we consider in our analysis is the 12-volt battery. So considering the sign convention over power sources, we can again, the sign convention for the power sources is based on the direction, the sign of the leaving terminal. Okay, so from here, our direction of travel is assigned counterclockwise. So when we go over the 12-volt battery, we are actually entering the negative terminal, and we have the positive terminal as our leaving terminal. So therefore, that is positive. The sign of the 12-volt value in our equation, therefore, should be assigned as positive. So this means this would be 12 volts. Okay? Okay, next. Let's have the 2 ohm resistor. Okay, so the 2 ohm resistor, this is our resistor. So therefore, in order to get the sign of the voltage for the 2 ohm resistor, we consider the sign conventions for resistors. So again, the sign convention is based on the direction of the travel assigned and the direction of the current that is flowing through the given resistor. If it happens that they are in opposite direction, the sign of the voltage would be positive and the IR term would be positive, while if they are in the same direction, the sign of the voltage and the IR term would be negative. Okay, so for the given problem, For the 2 ohm resistor, the direction of travel is towards this direction from right to left, and the direction of the assigned current is also going from right to left, so therefore they are of the same direction. So the voltage therefore for the 2 ohm resistor would be negative. So in our equation, this is 12 volts, so minus the voltage for the 2 ohm resistor, which is represented by the IR term. So this is 2 ohms okay, so 2 ohms multiplied by our current, which is assigned as I. So remember, this is your IR term. This is all by Ohm's law. The IR term represents your voltage. Okay, so what I'm going to do here is simply I'll be constructing the equation using the numbers only. I'll be removing the corresponding units so that we will be left with the symbols only for the numbers and the symbol for current. Okay, so instead of having this as 2 ohms times I, this is simply written as 2I. Okay, so this is 12 volts minus 2I. Okay, next. Next is the 3 ohm resistor. So again, this is our resistor. In order to get the sign convention for the voltage for the 3 ohm resistor, we consider the direction of travel, which is going over the 3 ohm resistor. The direction of travel at that point is going downwards. The current is also moving downwards, so they are still in the same direction. So therefore, the assignment of the sign for the IR term for the 3 ohm for this 3 ohm resistor would be negative. So this becomes 3I. So this means this is minus 3 times I. Okay, so next would be the 4 ohm resistor. So the 4 ohm resistor is resistor, so we consider the sign convention for resistors. Okay, so the direction of travel is still going towards from left to right, counterclockwise, and the direction of current is also moving towards the right in the same direction. So therefore, the voltage drop for the 4 ohm resistor is also negative. So this means in our equation, this becomes minus 4 times I. Next would be the 4 volt EMF source or the battery. Okay, so again, this is the power source. So we consider the sign convention when we do the travel for power sources. The sign would be assigned as the sign of the leaving terminal. Okay, so in our diagram, our direction of travel enters the positive terminal of the 4 volt battery, and the leaving terminal would be the negative terminal. So this means our sign for the 4 volt term in our equation would be negative. So negative 4. Negative 4. Okay, next. So finally, we end up the direction of our travel at the 7 ohm resistor. Okay, so still the direction of travel is in the same direction as the direction of the current. So the IR term for the 7 ohm resistor would be negative. So this becomes minus 7I. And the sum, as expected by virtue of Kirchhoff's laws, is equal to 0. So, given this equation, what would happen to our solution? This actually would sum up to, of course, 12 minus 4 gives us 8. Also, the terms with the i's would be negative 2, negative 3, so that makes negative 5. Negative 5 minus 4 gives us negative 9. Negative 9 minus 7 gives us negative 16. So therefore, combining these terms gives us negative 16i. So from here, we could actually transpose the term negative 16i to the other side, of the equal sign, rendering it as positive. So this becomes 16i is equal to 8. So from here, we can divide both sides by 16. Okay, so 16. Okay, so dividing both sides by 16, the 16 would be cancelled. So what is left here would be the solution for I. Okay, so of course, 8 over 16 could be reduced to lowest term by dividing both sides by 8. So what happens here now is that this becomes 1 over 2 amperes. So this means this is 1/2 amperes, or this in decimal form, this is 0.5 amperes. Therefore, we have already computed for the current that is flowing around our circuit, which has the value 0.5 amperes. So from here, we can now actually compute for the potential difference at points A and B. Okay, so how do we compute now for the voltage drop at point A and B? Okay, so this is the technique. Notice that you only have a single loop in our given problem, and the whole loop is divided into two branches, which is which we consider as the upper branch and the lower branch. We could assign the upper branch as this one, which includes the 3 ohm resistor and the 12-volt battery. And the lower branch would be this one, which includes the 4-volt battery and the 7 ohm resistor. So the idea here is that by virtue of Kirchhoff's loop rule, the voltage distribution of the in the upper loop and the in the upper branch and the lower branch should be should equal to 0. So if you're going to divide it into the voltage distribution among them, the sum of the voltage in the upper branch should sum up to 0 with the sum of the voltage of the circuit elements for the lower branch. So this means that if you're going to compute for the values of the voltages on the upper branch, that should be equal to the voltage of all the circuit elements in the lower branch, and that should be equal also to points to the voltage across points A and B, or V sub AB. So doing that, okay, so if you're going to compute for the total voltage of all the circuit elements in the upper branch, okay, so for the upper branch, remember that the circuit elements that are included in the upper branch are the following. You have the 12-volt EMF, you have the 2 ohm resistor, and you have the 3 ohm resistor. Now, knowing that the current is already computed as 0.5 amperes, we could actually compute for the individual voltages of each, starting with the 12-volt EMF. So that would be 12 volts. Next would be, okay, okay, so starting with the 12-volt battery, or the 12-volt EMF. Next would be the 2 ohm resistor. Okay, so for the voltage of the 2 ohm resistor, we apply Ohm's law. So Ohm's law is equal to V is equal to I times R. So I times 2 ohms. So we have plus so you have 2 ohms, 2 times 0.5 amperes. This is 12 volts. Of course, this gives us this should give us the the voltage drop for the 2 ohm resistor. And remember, in our given equation, we have the term 2i as equal to negative. So therefore, this is negative. Okay, next, we have the 3 ohm resistor. Okay, so considering the voltage drop for the 3 ohm resistor, we have 3 times I, so that is 3 times 0.5. Okay, so this becomes minus 3 ohms times 0.5. This should be equal to V sub AB. Okay, so this would be equal to V sub AB. Okay. Okay, so for V sub AB, this becomes, of course, 2 ohms times 0.5. This becomes 1 volt. Okay. Next is 3 times 0.5. This becomes 1.5 volts. Okay, so doing the sum. Okay, so of course, 12 minus 1 becomes 11. 11 minus 1.5 gives us 9.5. So this means that the value of the voltage across point A and point B is equal to 9.5 volts. Okay, so perhaps we could verify our answers by also computing for the voltage drop for the lower branch instead of the upper branch. Okay, so for the lower branch, we have 4 volts. Okay, so 4 volts would be negative since our direction of the travel would be this one. Okay, so we have negative 4. Okay, so next we have negative for the 4 ohm resistor. We have the IR term for the 4 ohm resistor. We have 4 times 0.5, so that would be negative also in our equation. So this would be negative 4 ohms times 0.5 amperes. Next would be for the 7 ohm resistor, so 7 times 0.5. This would be 7 times 0.5. This is expected to be equal also to V sub AB. Okay, so we have now here as the solution as negative 4 volts. Next is negative 4 times 0.5, that gives us 2 volts. Next is 7 times 0.5, that is 3.5 volts. Okay, so considering the sum, this becomes negative 4 plus negative 2, that is negative 6. Negative 6 minus 3.5 gives us negative 9.5 volts. Okay, so the overall value now for V sub AB is of course 9.5 volts. Now, considering the sign, what does the positive sign for V sub AB mean? And what does the sign negative 9.5 for the lower branch mean? This means that this basically proves the rule for Kirchhoff's loop rule, that when you do the algebraic sum of the voltages for all circuit elements around the given loop, the sum of those voltage drops should equal to 0. So meaning, if your upper branch is renders a sign of the voltage as positive, therefore, in order for it to equalize to 0, the lower branch should compensate for that value, but has the opposite sign, so that when you add them together, you will end up with the value for the sum of the voltages of all the circuit elements around the loop as equal to 0. But as for our answer for letter B, the value of course for V sub AB is equal to 9.5 volts, which is in absolute value, since we're only getting the magnitude of V sub AB. Okay, so for that, this is for letter A, this is for letter B. Now, as for letter C, the power output. For letter A, current through the loop. Okay, so this is for letter B is for V sub AB. Letter A is for the current. Okay, so for letter C, okay, so the power output of each EMF. Okay, so to compute for the power output of each EMF, we need to recall that um, the power output is given as equal to the power output is given as equal to V times I, or I times V. Of course, this was already discussed to you from the previous discussion on EMF. P is equal to IB. Now, recall that also we have V is equal to IR for Ohm's law. So we have the different forms now for our equation for P is equal to IB. If we're going to replace I, for example, with V over R. Okay, so let us replace first V with I times R. So therefore, you have I times R replaced for V. This becomes I times I. That gives us I squared times R. Okay, so this becomes I square times R. Or, for example, instead of replacing V with the IR term, we could actually replace I instead by the V over R term coming from Ohm's law also. So, doing that, the the formula for power becomes okay, so this becomes R. Okay, so this becomes V squared. Okay, so considering the different forms of the formula for power, P is equal to IV, which is also equal to I square R, is also equal to V square over R. Now, of course, the different forms provides us enough choice of combination of terms so that we can alternately compute for the power drops of the power output of each battery. Okay, so to compute for the power output of the 12 volt resistor, the 12 volt EMF, we consider, of course, the internal resistance of the battery, which has a resistance of 2 ohms. Remember that the current flowing through the battery is also is given by zero point 0.5. So therefore, the power output of the 12 volt battery is equal to V square over R. So considering or making use of V square over R. Okay, so this becomes V square becomes 12 volt square over R, which is 2. Okay, so this becomes, of course, 12 square becomes 144 over 2 gives you, that would be 72 watts. Now, if we try to compare this with the other different forms of the equation for the power, so for example, instead of having P is equal to V squared over R, we have I times V. So we have, of course, I times V means that you have the zero point 0.5 ampere current, and you multiply this with V, which is 12 volts. Or perhaps you could use this other form, I square R. Okay. So I square means okay, so I square is 0.5 amperes square times R. Our R is 2 ohms. So this should give us 0.5 as 1/4. 1/4, you have 2 over 4, gives you 1/2 or zero point 0.5 watts. Okay, so 0.5 watts. Now the other form, okay, so let me just complete the whole set. Okay, so the other form is I times V, I times V. So this means this is given as 0.5, 0.5 amperes, and you multiply this with V, which is 12 volts. So this is given as 0.6. This is 6 watts. Okay, so this is 0.5 square is becomes 0.25. 0.25 times 2 means 1/4 of 2. Okay, so you have zero point 0.5 amperes, zero point 0.5 times zero point 0.5, then times 2, you have 0.5 watts. As for P is equal to I times V, this becomes zero point 0.5 times the voltage across the the 2 ohm resistor. This is actually the 2 ohm resistor is 2. You have 2 times um, 2 ohms times this is 0 0.5. So basically what happens here is this becomes 0 0.5 watts. Now as for this one, this is actually the voltage across the R resistor is given as 2 times zero point 0.5. So this is 1 square. Of course 1 square is 1 or 1 half. So this becomes 0 0.5 watts. Now, in this computation, what you see here is we have computed for the power output across the internal resistance R in the 2 ohm resistor. Now, to compute for the overall power output of the battery would come from the sum of the voltage of between the EMF source and the voltage drop provided by the 2 ohm resistor. So this means that the overall power output of the battery, remember that the battery is composed of the 12 volt EMF and the 12 internal resistance that is 2 ohms. So therefore the power output is not necessarily equal to 12 volts only, but 12 volts minus the um, voltage drop in the 2 ohm resistor. So therefore the overall power output of the 12 ohm resistor of the 12 volt battery would be, okay, so let me just label this as the power output of the 12 volt battery should be equal to 12 volts minus should be equal to I times V minus 0 0.5 watts. Which is basically equal to, okay, which is equal to okay, so I is 0 0.5 amperes and the voltage would be 12 volts. So minus 0 0.5 watts. Okay, so what happens here is this becomes 0 0.5 times 12 gives us 6 watts. Minus 0 0.5 watts gives us okay, so this becomes okay, so 5.5 watts. Now this is the power output for the battery, which again is composed of the 12 volt EMF and the 2 ohm resistor. So the idea here is to get the power output, simply you get the difference in the voltage of the two, then you multiply it with the current. The resulting power output would be the power output of the battery. Okay, so an could also be that could also serve as an alternate solution just to check whether your solution is correct. So for example, if you're going to compute for the voltage of the 2 ohm resistor, the voltage drop of the 2 ohm resistor would be that would be I times R. So that would be I times R, that would be negative 1. So minus, you subtract that from 12 volts, so that gives you 11 volts. You multiply 11 volts by 0.5. Okay, so 11 times 0.5, that gives you 5.5 watts, just like what we have computed here. So 5.5 watts. Okay, so as for the next set, for the next battery, okay, so again, we have P is equal to V squared over R um, for the 4 ohm resistor. So this would be um, the voltage across the 4 ohm resistor is given by, that would be negative 4 times I. So negative 4 times 0.5 gives us negative 2, or 2. So this becomes 2 over 4 as the resistance in ohms. So this becomes 4 over 4. And this becomes 1 watt. Okay, so let me repeat that again. So this becomes 2, this becomes 4, this becomes this becomes 4 over 4, and this becomes 1 watt. Okay, so doing the second form of the formula for power, instead of making use of V squared over R, we have I squared R. So this becomes 0.5 amperes times the resistance R, which is 4 ohms. So 0.5 becomes 1/4. 1/4 of 4 gives us 1 watts. Okay? Okay, so as for the first form, we have I times V. So this is point, 0.5 amperes multiplied by 2 volts. This becomes 1 watt. Okay, so let me just complete the set of the solution. Remember that the voltage for the voltage across the 4 ohm resistor is given as 2 volts, and 4 here is the resistance. This is actually 4 ohms. As for the first solution, this is actually the voltage is equal to 1 ohm, 1 volt over 2 ohms. So that becomes 1 over 2, or 0.5. Also, this is equal to 1 volt. 1 volt. So that gives you 0.5 watts. Okay, so to continue, we have now the power output for the 4 volt battery. Okay, so we have IV minus the output of the power output due to the presence of the resistor. So we have IV, which is zero point 0.5 times 4 volts minus zero point 0.5 or minus 1 watts or 1 watt. So this gives us zero point 0.5 times 4 gives us 2 watts minus 1 watt. So finally we have here as equal to 1 watt. Remember, this is the power output for the 4 volt battery. Okay. Okay, so to continue, okay, so find the current I, the internal resistance R, and the EMF in the given figure below. Okay, so I will not be presenting to you the solution for this problem, the idea, but I'll just be presenting to you the idea. The idea here, in order for you to compute for the what is missing, the current I, the resistance R, and the EMF E, is to apply the same technique that was presented earlier in the first problem individually for all the present loops in the given problem. So for example, you have loop number 1 here in the direction of travel that is clockwise. Loop number 2 is also clockwise. Loop number 3 is also clockwise. So what we have done in the analysis for the first problem, you will be applying those individually for all the loops present here, and eventually you would end up with simultaneous equations. So what you do with those simultaneous equations is to solve them using solutions to linear equations. Okay, so of course this idea is of higher mathematics, and I expect that you already know even the most basic of all algebraic solutions. So I am assuming that you, since this subject is already an advanced subject, you are assumed to have assimilated advanced knowledge in computation, such as when I say that you solve this using solutions to linear equations. Of course, I assume that you already know those solutions. The solutions making use of elimination, substitution, simultaneous equation, or making use of the matrix. Then you just simply apply those solutions in order to solve for the missing quantities here. Okay, so just like what is presented here. Okay, so again, you are given the direction of the loops and the direction of travel. So what you're going to do is to apply the pattern of solving for the solution that we have done from the previous problem in each of the identified loops in this problem. Okay, so for you to compute for what is being asked in this problem as I, R, and the EMFE. Okay, so this ends our topic discussion for this part of our lecture series on Kirchhoff's laws.